Welcome to our third pre-lecture for Physics 264. I'm Dr. Steve Brule. Today's topic is Thevenin equivalent circuits and getting real with breadboards. Let me get my pen going here. First, we'll see why the Thevenin equivalent circuits are useful. Then we'll review Norton equivalent circuits and see why they come in handy sometimes. We'll learn how to use a breadboard to set up real circuits, which is what we'll be doing in lab this week. And we'll learn how not to break multimeters when we're working with them. And we'll see what it means for a power supply to have a floating ground. Well, remember this circuit from last week? I'm sure you couldn't forget with all these elements. We used Kirchhoffs Law to find the currents through every element in this circuit, and it was a lot of work to solve all the simultaneous equations. Here we're showing a voltmeter measuring the voltage across this resistor. In our lab, we measured the current, or we calculated the current, but we could have easily used that current to calculate the voltage, as we will do today. Okay, to work out the Thevenin equivalent circuit for this circuit, first you remove an element in the circuit of interest, and I'm just picking this arbitrarily to say R5 is our element of interest. We could have used R1, R4, R2, whatever we want. So we're using R5 right now because we're interested in making the Thevenin equivalent circuit for this business. Okay. Now we'll use whatever technique we know how to use to find the open circuit voltage between these two junctions where we've removed the element. So we're going to try to find the voltage between these 2 points using whatever method we want. And I'm going to go through this pretty quick because we did this last week, but just for a review, here we go. I'm going to use Kirchhoffs Law to find the current through R3, and once I know the current, I'll know the voltage, and then I'll be able to find the voltage around here using a Kirchhoff loop. While writing all the currents in this circuit, we see that there's no current that goes through the open circuit here. So all the current is I bypass through that, and we just have I2 coming through this circuit because they're all in series. And you see that I arbitrarily picked this direction for I2, but it turns out to be wrong, as we'll see. Okay, so I went through, and I'm not going to talk about how I found the 3 equations because we're trying to move fast here, but I did a junction rule and 2 loop rules. Got these 3 equations, and that turns into this matrix for putting into MATLAB. Put it into MATLAB, and then MATLAB told me that I2 was negative 1.6 milliamps. And whenever you get a negative sign when you solve those simultaneous equations, it means that the current is really traveling in the opposite direction. So we could either say it's negative 1.6 going in this direction or positive 1.6 going in that direction. And we'll think about it in terms of a positive current for the remainder of this show. Okay, so once I know the current through R3, I can calculate what the voltage across R3 is just using Ohm's law. The current times the resistance of any resistor will give you the voltage across that resistor. Now I'm going to use a Kirchhoff loop to go around this loop to find out what the Thevenin voltage is. And I arbitrarily pick this side as negative and this side as positive. I don't know what the Thevenin voltage is, but I just have to assume something. And if I get a negative sign, I know that I assumed wrong. So writing Kirchhoff's loop for this particular loop, I go up 12, so that's positive 12. Whenever I'm going in the same direction as a current through a resistor, I drop voltage. So there's the voltage that I dropped. I already calculated what that was, so it's minus 3.2 volts as I go through that resistor. And now I'm going up Thevenin's voltage because I'm going from negative to positive, so I'm going to enter that as a positive voltage here, and then I end up where I started, which is 0. Solving for Thevenin's voltage here, I get negative 8.8. So once again, I guessed wrong with my polarities. So I guessed that this was going to be negative and this is going to be positive, but it turns out it was just the opposite. So if I get negative 8.8 for this polarity, that's the same thing as positive 8.8 for this polarity. Okay, so now we have our Thevenin's voltage, and I just hooked up multi-sim really quick to check that, and sure enough, it is 8.8 volts when I have my positive terminal here and my negative terminal there. All right. To find the Thevenin resistance, we must remove all the batteries from our circuit. So we have 3 batteries in this circuit, and we're going to replace them with short circuits or wires. So watch those 3 batteries. They'll disappear and turn into wires. Now I just want to find the resistance between these 2 points. Can you do that? Why don't you press pause and see if you could find the resistance between those 2 points. I'm going to do it for you real quick. Okay, here we are back. I hope you worked this out. And notice that these 2 resistors are in parallel because they're holding hands. So we use the equation for parallel resistance to get R14. Then we notice that these 2 resistors are in series, because anything that goes through one has to go through the other. So I use the series formula for series resistors, add them together, I get this. And now I notice that these 2 are in parallel, and I use the equation for parallel resistors to find out the final resistance here. So the Thevenin resistance is 933 ohms. And I check that with multi-sim, and sure enough, it is 933 ohms. So now that we have our Thevenin voltage and our Thevenin resistance, we can replace this entire circuit with a single resistor and a single battery. So that turns out to be looking like this, with the resistor in series with the battery. So there's my Thevenin resistance, there's my Thevenin voltage. Well, why did we do this? It's because now that we have this circuit simplified to this, now whatever resistor we put in here, it'll be very easy to calculate what voltage is across that resistor from these 2 quantities. So I put in the original resistance that we had in the circuit, which was 500, using the voltage divider equation here, which is to find the voltage across this resistor. It's the 500 ohms over the total resistance, which is the resistance in series, multiplied by my Thevenin voltage. That gives me 3.07 volts, which is what we measured in the circuit way back at the beginning of our show. Well, just to show you how useful this is, now I plug in 3,000 ohms for my mystery resistor, put that 3,000 in my voltage divider equation, and I've got what the voltage is. And it turned out to be the same as what multi-sim gives me. So now, instead of having to go through all our equations and solving those equations simultaneously again, we can very quickly find what voltage we have across that resistor. And I did it just one more time for a very large resistor. There's 100 kiloohms, and put 100 kiloohms into our voltage divider equation, and we get a voltage that's very close to our Thevenin voltage. And I verified that with multi-sim once again. Well, we can do an analogous process using a Norton equivalent circuit and quickly find current instead of voltage in some circuit. So here's that equation, or that circuit once again, and we've removed the element of interest, but now we replace that element with a wire, a short circuit, and then we're going to calculate what the Norton current is using whatever methods we can come up with to find that current. You could go through and use Kirchhoffs laws, and it would be kind of a long process, and where you'd have to solve for all those equations simultaneously again. I just hooked it up with a multi-sim and got what, and this is what you're going to do in lab this week as well. I just hooked up a meter in series with this current. So any current coming through here has to go through that meter and then go through the battery. And I measured it to be, well, in the simulation, 9.428 milliamps. So now we have our Norton current, and we put that current, this is a constant current source, so that battery would have a variable voltage supply. So that battery would do whatever it takes to keep 9.428 milliamps going through whatever we put across the load for that battery. And it turns out that there are things like this in real life that we actually use constant current sources. So the Norton circuits are useful. So right now, it would just be putting the 9.428 milliamps through our Norton resistance, and we notice that the Norton resistance is always the same as the Thevenin resistance, so we don't have to even talk about that. You calculate it in the same way you calculated the Thevenin resistance. Well, now I've plugged in the original 500 ohms for my mystery resistance, and now we can find the current through that resistance using the current divider equation. In the current divider equation, instead of putting this resistance over the total resistance, I put this resistance over the total resistance. So I put the 933 over the total resistance, then multiply it by the total current coming out here, and it tells me how much current is going through this element right here. Then it says that it's 6.14 milliamps. Sure enough, it's 6.14 milliamps when I tested it in multisim. I changed the resistance just to show you how useful this is. I changed it to 3,000 ohms. All I had to do is change one term in my current divider equation, and I got the the new current through this element. And once again, this is simulating that big, huge circuit. Now that we have Norton's current, we don't have to go through all those simultaneous equations like we did in last week. Well, Thevenin says if you have a Thevenin circuit and you put some resistor in here, like the 3,000 ohms that we just did, well, you use a voltage divider equation to find the voltage across that resistance, and then you could very easily use Ohm's law to find the current through that. But we're learning Thevenin as well because there are times in real life where we have a constant current source and it's more convenient to use Thevenin to use Norton rather than Thevenin for those constant current situations. Most of the time we'll be using Thevenin. Okay, well, let's jump into what we're going to do in lab this week, and this is very important because you have to learn how to use these different materials in our lab. So this is a breadboard, and here's the power supply for our breadboard. The power supply, when you hook it into this little connector, I think that's called a DIN connector, we get, there's connections underneath here that give us a 5-volt from this power supply. And you're going to learn how to create your own power supply in this class. What's in this black box, you don't know now, but you will eventually. So what comes out of this is 5 volts across this rail. They have to use a little jumper here because these are all connected, these are all connected, but then you need a jumper to connect that across. So everything that and every wire you connect in one of those little holes will be at +5. Every wire you connect in one of these holes here will be at the ground. Every wire you connect in any one of these holes across here, and there's the jumper, any one of those will all be at +12 volt, and any jumper or any wire you put in here will have a voltage of -12. And each one of these voltages shares the same ground, and that's very important, as we'll talk about at the end of the show today. When picking wires, just to keep things clear, and it's much easier for us to know what we're doing. I did these circuits for a year. I did this for a living, breadboarding different circuits, and this is the technique that I always used. Whenever I was connecting a wire to a ground, I always used black. Let me show you what that would look like. So any wire that say if I want this row of connectors, all those are connected together. Well, let's say I wanted this to be connected, some element that's in this row of connectors to be connected to the ground. Well, I'm going to connect a black wire over to here and stick it in that little hole, and now every one of these holes is also at ground. And if I used pink there, then the color coding doesn't help us when we look at the circuit. We can't quickly look at the circuit and analyze what's going on. So then whenever we connect to the +5, we're going to get come on, slowing me down here. we're going to connect. So if I wanted, say, this row right here to be all at positive 5, I'd connect an orange piece of wire into one of those holes. Likewise, dang, why does it do that? If I wanted anything to be at plus 12, I'm going to come down here at plus 12. Let's say I wanted this row right here to be at plus 12. I'm going to bring a red wire over there and bring it there. And you'll see the why this is useful as we get more complicated circuits and you're trying to analyze what's going on. When you see this black, you always know that that's going to be ground. When you see this red, you know that's going to be the plus 12. And if you saw a blue, then you would know that anywhere that's connected to this blue, let's say I wanted this row to be blue, I'd connect a wire there. So anything in here is going to be at negative 12. All right. The rows are connected. I already told you about that. The rows are connected like this. These are connected long ways. We'll be using Radio Shack multimeters. You might think Radio Shack is cheap, but they work fine. Our breadboards have these handy connectors down here for banana plugs, so we connect the meter into these connectors, so then we can have a wire that then sticks into one of these holes, and we can then it's an easy way to keep things nice and tidy. We could have a wire that's connected onto this big banana wire here, but it becomes very clumsy. So we just connect them into here and then run a wire wherever we want. Here's somebody where they're they've got the meter hooked, the multimeter hooked to voltage or switched to voltage, so it's measuring a voltage, and then the multimeter is of course stuck into these two terminal posts. And then the red one is going here to our plus 5 supply. The black one's going here to the ground, and the person is reading 5 volts, just like they should. What do you think would happen if this person just switched their meter over to, instead of voltage, they measured current? Let's see, right here. So if they just put it one notch over, wouldn't it just measure the current through the supply, the total current? Press pause and see if you could figure out what's wrong with that picture. Well, the problem is that if you put your leads directly to the power here, you're not measuring you are measuring the current through the power, but since the meter itself has zero resistance or very close to resistance, it draws a huge current through your meter, and then that current will cause the meter to either break, or if the meter has a fuse in it, the fuse will blow, and then we have to get a screwdriver and undo it, and it's a big hassle. Here this person is just hooking. This is what usually happens in lab when this disaster happens. Some student will say, oh, I want to know what current is going through that resistor, and to find current, they'll just put it in parallel. Well, you do put a meter in parallel to measure voltage, but if you want to find the current through this resistor, you have to break the circuit and then put your meter in the circuit that way, so that all the current must go. This way the current comes from the 12-volt supply, goes right through here, comes out here, and bypasses the resistor, because the resistance has more resistance than your meter, and it would blow the meter. Here is our fearless leader showing us what happened last year when students plugged a power rail, so they connected the the ground to one end of this using a black wire, we would do, and let's say they just connected the positive 5 right here. So they just connected the positive 5 to ground and ran it through that little connection row. And these breadboards are not designed to take large currents, and it actually burned the breadboard and ruined it. We couldn't use it again, and that cost our department $100. So that was another thing you should never do. And finally, never set a meter to read resistance. So if you wanted to say, oh, I want to read the internal resistance of my power supply, I'm just going to set this to ohms. Well, you can't do that, because the meter works by putting out its own voltage, and then it's putting out a voltage onto the voltage of your supply, and they're fighting each other, and it's not going to like it, and it could also break your meter. So don't do that. So always check that you're not shorting the power supply before you turn the meter to measure current, or before you turn it to measure ohms, make sure that there's no battery in the circuit. Finally, we're going to talk about this floating ground situation. Let's say we wanted to set this circuit up. Oh, we're not going to talk about that yet, because we're just going to talk about, well, how would we set up such a simple circuit? So let's take a look at that. Maybe press pause and see how you would set it up. Okay, welcome back. So we've got the 12-volt supply going through on the positive side of my power rail. It's going to R2 and R3. So I've got the positive side. Here it is right here. I've got the wrong color for plus 12 because I'm going to be using red for that. So here it is, red all the way across here. Then the red wire comes over here, goes to one side of our, what was that, 2 and 3? I don't remember what I named them. But it's going to one side of the parallel resistors. And then here are the parallel resistors all connecting to the same little row there. And then I plug the third resistor into that row. And now that makes a junction there for those 3 resistors. Then the current comes out of that resistor and goes back into ground. Let's just check and see that that's what happened. So here it is going to one side of the 2 resistors. Here's that junction that is right here. See, it doesn't look anything like what we observed. This doesn't look like the circuit really, so you got to get used to doing this. And then the other side, there's that junction, and it goes over to ground. And let's see if it does in here. So there's the junction. It goes through the R1 into ground. And then the ground, I'll just point out that the ground here is connected to the power supply here, but I keep pushing the wrong button. Sorry about that. Here, this ground, you don't have to connect to the circuit. That's only for the multi-sim, because in our circuits, the negative terminal of all of our supplies is hooked to ground, except for the negative side. Then it's the positive one that's hooked to ground. So it's already hooked internally to ground. Here's that same circuit, and then I kept flashing at you. This is the same exact circuit, but now we've got our meter hooked across that R1 at the bottom to measure the voltage across that resistance. And here it is. There's my meter leads going over to measure the voltage across the parallel combination of resistors. Here's the same circuit. Now this is important. If you want to measure the current through these 3 resistors, here that is, you have to break. See, this used to be going directly to the plus 12 rail, but we have to break that connection so that any current that comes through these 2 has to go through my meter. It's going backwards through the meter, but that's all right. And then from the meter, now it's going to come over to the rail. So we broke. All I did was I took this to measure current. This wire used to be hooked in here. Let's go back in time and see that it was. See? It was hooked in there. And then I just unhooked it. And then I put it over to this row. I could have used any one of these rows, but I used that one. And then I put, now that it doesn't form a complete circuit, because here's the ground and here's the resistors, and there's no current that can flow through them because it's not going anywhere. But I make a path that goes through the meter, and the meter is now turned to measure current. So always, before you turn that meter to current, always check to make sure you're not in parallel with something that could, some voltage that could send a huge current through the meter. If you're ever unsure of resistance, like if you're not good at measuring the color code, which I've done electronics all my life and I still don't know it, I just use a meter to check the resistors, and this one is at 1K. And it's actually better than the color code because it gives you the resistance to 4 significant figures. And there's each one of these resistors will vary according to its resistance. Never turn your meter onto ohms when you have the circuit live. Like, let's see, like this circuit right here is hooked to a power source. We couldn't just try to measure the resistance of that resistor with our ohm meter because there's already current going through there. And remember, our ohm meter sends its own current through it, and it'll start fighting with our power supply, and they don't like it. Okay. Finally, we talk about what a floating ground is. So we need to be careful when hooking up circuits with multiple power sources because if we don't have independent power sources that have floating grounds. And what we mean by that is, in our circuit right here, all these rails share the same ground. So that means that this terminal right here is hooked to ground even though you don't see it. And this terminal is hooked to ground because I already put it in from multisim, but it's hooked in and it's invisible. So these terminals are hooked invisibly to ground. So we could hook this circuit up and it's fine because these are already hooked to ground, so if we hook them together, no problem. But if we try to do this circuit where I've got the plus 5 volt terminal connected to the negative terminal of my 12 volt supply, well then that is, this is already to ground and this is to ground. So what we're doing is we're shorting my 5 volt power supply to ground, and it's going to cause great problems and blow burn that out. Okay, so always check yourself before measuring current or resistance with a multimeter to make sure that you don't, for resistance, you don't have a live circuit, and for current, you're not in parallel with any element that could cause you to measure large currents. Well, what did we do today? We saw why the Thevenin equivalent circuits are useful. We reviewed Norton equivalent circuits and saw that they'll come in handy one day when we're talking about constant current sources. We learned how to use breadboards to set up our real circuits, and we learned how not to break multimeters when measuring currents, and finally we now know what it means to have a floating ground. Let me just go back real quick. So this circuit that I said that you could not do, you could do if you had two independent power supplies whose ground was floating. That means if the ground is floating, that means that this terminal and this terminal are not connected internally to ground. And then if you had two power supplies that had floating grounds, you could hook them up like this and it would be no problem. Usually they're more expensive, those kind of power supplies. I hope you've enjoyed the show today. Let's see, how do I stop this?